Hello, Professor. I'm Navya Koduri. I'm here to present a PPT on the research paper which I have selected. Let me share my screen to show you the PPT which I have done. Sorry. Yeah. This is the PPT which I have prepared from the research paper which I have taken. And the title of the research paper that I have taken is SRNIC, a scalable architecture for RDMA NICs. And these are the authors' names which are visible below the architecture, below the title of the paper. And also, let's go to the introduction page. That is here. It gives a brief introduction about the paper SRNIC. Now let us go deep into the introduction. That is, in order to solve the scalability issues with RDMA NICs in data center networks, this SRNIC is a unique architecture. This architecture will help us to resolve the scalability issues which the others were faced in the existing systems, that is RDMA NICs. And also it retains the great performance and the minimal CPU overhead when enhancing the scalability of both the network and the connection. And also the full form of RDMA is direct remote direct memory access. This is a well-known technique which is used for high-speed networking. And also the large-scale data centers impose challenges to the scalability of NICs, which is RNICs. And coming to the RDMA overview, RDMA is the overview is by avoiding the kernel and assigning the transport functions to the hardware. RDMA offers fast throughput and the low latency and the low CPU overhead. It offers very low latency and CPU overhead by avoiding kernel and assigning transport to functions. And also a lot of contemporary data centers use ROCE V2, that is RDMA over converged Ethernet version 2. And this RDMA over converged Ethernet version 2 depends on PFC, that is the priority based flow control, which makes the network scalability a challenge. By using PFC, a challenge will be created to the network scalability. And most of the ROCE version, that is RDMA over converged Ethernet version 2, depends on PFC, that is priority based flow control. And going to the next slide, that is let us discuss about the problem identification, where the problem was identified. That is in the paper which I have taken, I have observed mainly two problems with RDMA analysis. Those are the network scalability and the connection scalability. Uh, Let me give you a one line idea of network scalability and the connection scalability. That is the network scalability. Firstly, the network scalability means it head off line blocking and PFC storms are the examples of the problems with the network scalability in the large networks. And coming to the connection scalability, the RDMA performance decreases as the number of connections increases due to connection scalability. By increasing the number of connections, the RDA performance will be decreased due to the connection scalability. And going to the next slide, let us discuss about the existing solution. What is the existing solution for this problem? That is the commercial RNAs have high performance, but but having scaling problems with their networks and the connections. Those are by RN removes PFC. Mainly the PFCs, the priority based flow control, is the majority problem, which is removed by the INR, and which increases the network scalability, but does not. In the previous existing solutions, most of the others have focused on to remove the network scalability, but they doesn't address the connection scalability. And also the commercial RNICs have performed very greatly with the networks and the connections, but have the scaling problems. Those are the network scalability and the connection scalability. uh, this is the existing solution as far as now. And let us discuss the overview architecture of the paper which I have selected, that is SRNAC. Mm, this is the architecture overview. Firstly, the goal of SRNAC is to handle the connection scalability by preserving the low CPU overhead and the good performance. This is the main aim of the SRNAC. That is to handle the connection scalability by providing low CPU overhead and good performance, and also achieves a great connection network scalabilities by combining it combines the advantages of IRN and the commercial RNICs. By combining these two advantages, it achieves the great network and the connection scalabilities. Uh, Let us discuss about the architecture, that is the three layer. It has a three-layer architecture of RNIC hardware. Those are basically the basic NIC, transport, and the DMA engine. Let us discuss one by one. That is, firstly, let us discuss about DMA engine. That is, the DMA engine schedules tens of thousands of QPs from the host memory using a QP scheduler. It selects which QP to transfer the data to the next and uses the data to move over to the retro EMC WQEs and the data from that SQ. That is here the main role of DMA engine layer is to schedule the thousands of QPs using a QP scheduler, and it selects the QPs to transfer the data from that SQ. With the exception of the software retransmission in the CPU, the majority of RDMA transport functionalities are released by the transport layer. And the transport layer is the main goal of the transport layer is to transport the functionalities of RDMA, and it retransmits in the CPU. And also the functionalities include a hardware retransmission module that implements the hardware portion of selective repeat and a conjunction management, and also that implements a DC TCP, that is the hardware friendly. And the major part is sending and receiving ROCE 2, that is the version 2 packets over 100 GMAC is the major responsibility of the basic NIC layer, which carries the core operations of Ethernet NICs. This is the working architecture of SRNIC. And let's go to the another slide. Uh, that is the key innovations. It mainly focuses on two key innovations. Those are cache-free QP scheduler and memory-free selective repeat. Firstly, let us discuss about cache-free QP scheduler. The main aim of a cache-free QP scheduler is to remove the requirements of QP contents to be cached on chip, and also the memory free selective repeat is helpful to manage the packet losses with the memory usage. By using this memory free selective repeat, it manages the packets with the very minimal memory usage. And also going to the next slide, that is cache free QP scheduler. Let us discuss about the cache free QP scheduler. That is the common data structure are optimized for RDMA designs, lowers memory needs by carrying out with a QP content on chip caching, and also it improves the scalability of the connections. It also improves scalability of connections. It overcomes the connection scalability mainly. And also the next slide, that is a memory free selective repeat. This memory free selective repeat helps to change the protocol to reduce the packet losses with a extensively increasing the memory usage. And also adjust the RDMA protocols header to effective manage packets losses, and reduces the memory usage through bitmap on loading and other methods exclusive to RDMA networks with loss. And coming to the implementation of SRNAC, that is created in FPGA prototype for an SRNAC that is completely operational. A prototype called FPGA is created that is operated on the overall systems. And also the on chip memory of the prototype is nearly 4.4 MB. And it attains the CPU overhead performance and the scalability design objectives too. This FPGA prototype is mainly developed to reduce the connection scalability time and the network scalability, the issues which I have discussed before. And connection scalability is not addressed by the previous others, but this paper is mainly focused on reducing the network scalability and the connection scalability. Attains a CPU over, and it also attains a CPU overhead performance and the scalability design objectives. And also uh, it even does not slow down, the system even does not slow down when it's supporting 10,000 connections. With a relative minimal CPU utilization, a prototype was able to reach a high data throughput of 97 Gbps and a low delay of 3.3 microseconds. It has never any complaints about the down of the server. It never gets slowed down uh, whenever treating with the large number of connections. And also the high data throughput is of 97 Gbps, and it has a low delay of 3.3 microseconds. 3.3 microseconds is its low delay uh, when it is working on the large number of systems, or even though it working on the large number of systems, its low delay is only 3.3 microseconds. 3.3 microseconds, yeah. And it's a high data throughput is 97 Gbps. This overall achievement demonstrates that sRNAC is capable of resolving RDMA scaling issues, RDMA and AC scaling issues. By the achievements of sRNAC, it is very sure that it can overcome the issues which are faced in RDMA and AC's RDMA and AC architecture. The provided sRNAC is a architecture is far better than the previous architectures that are RDMA and AC's architecture. This sRNAC architecture is the combination of NIC and RINC. This combination has become greater exposure to the network to overcome the network scalability and the connection scalability. And also going to the next slide, that is let us discuss about the performance evaluation of the provided paper. That is coming to the performance evaluation, It maintains over 10,000 efficient connections without experiencing any drop in the performance. Uh, it can hold a large number of connections by without a drop in the performance, and it also has an 18 times higher normalized stability connection stability than the commercial RNICs. uh, Previously I have said you about RNICs, which is this sRNIC is the combination of NIC and the RNIC. The provided system is 18 times better the provides 18 times higher normalized connection stability than the commercial RNICs, and it also has a low uh, delay. Even though it is working with the large number of systems, it has a low performance delay. It has very minimal performance delay, which is very quite manageable. And also it is a 18% higher normalized, it has an 18% higher normalized connections than the connection stability than the than the commercial RNICs. And also it has it can, with the less than 5% CPU overhead, it can maintain the overall connections. And also the maximum throughput of it is 97 Gbps, and the low latency is 3.3 microseconds are achieved, and 3.3 microseconds are achieved. And going to the next slide, that is let us compare the scalability, uh, that is scalability comparison. Coming to the scalability comparison, yeah, that I have seen during the previous slide, it has 18 times better normalized connections than the RNICs, and compared to and it also has 18 times better with sRNAs compared to Malconic CX5 uh, operations. Uh, it is far much better than the Malonix CX5. And let us discuss about the high tolerance of the provider system. That is, it has 3 times good throughput than the Malonix RNICs, and it has a very low, that is a 1% loss rate. That is 1%, and the good rate is very higher than the Malonix RNICs. And it is has a consistent performance on big and lossy networks. Even though it works on the large networks, it provides a consistent performance by having the low latency and a good throughput. And also these are the scalability comparisons. And let us analyze the design space. That is it says that high performance but limited scalability characteristics commercial RNICs. And when compared with INR unaddressed it unaddressed the connection scalability, but high network scalability. INR used to provide high network scalability, but it does not provide any connection scalability. Now, the high network and the connection scalability is achieved by this system, that is sRNICs. The currently produced architecture, that is sRNIC, achieved both the network and the connection scalability. It is given in the design space, which I have analyzed about the designs. In the previous, there is only they focused on only the network scalability, and the connection scalability is not addressed. But now the system, the architecture, that is sRNAC, achieved both the network and the connection scalability. And finally, the conclusion of this the provided paper is, let us come to the conclusion. That is superior scalability is achieved by combining the advantages of RNICs and IRN. By combining these two, the sRNIC is produced. Uh, by the sRNIC, the scalability has both the scalabilities, that is the connection scalability sorry, is achieved. As RNAC maintains the great performance and low CPU overhead, while addressing the connection scalability issues in RDMA analysis. Both the network scalability and the connection scalability is achieved, and also it offers the low CPU overhead while even addressing the connection scalability issues in RDMA analysis. And also the significant performance and the stability gains are shown in the fully functional prototype. Mm, this is the conclusion of the paper, that sRNIC has achieved both the connection and the network scalabilities. And let us discuss about the future enhancements of this paper, that is the future work. The next slide is the future work, that is in the future we can add more additional sRNAC optimizations for larger sizes, more functionalities, and also more options can be given in future for the larger, very large size of systems, and also combination with additional network technologies. We have only the network and the connection scalability now, but we can add the combination with the additional network technologies too, and examining different uses and applications. This sRNAC can be in future can be used on the several use cases and the different use cases and applications. And also attempts to enhance the design functionality through additional optimization, and finally a lot of testing in actual situation will contribute to ensure the successful applications of sRNAs. This is the overall the future work which I have thought by reading this paper. Yeah, finally, thank you. Uh, Thank you, Professor, for giving me this opportunity. I I believe that I have explained all the PPT which I have made, and which and I have given you the answers. I mean, I have explained the content which I have understood. Thank you. Thank you so much. Let me stop my share.